Okay, thank you, everybody. It's great to be here, and it's always fun to hear colleagues speak, even though we work in related things, especially with COVID, as Jinwa mentioned. It's nice to sort of come back after a break and hear, see people again in person, but also talk to colleagues and everybody else. So this is a shift in mode of transportation. I'm going to be talking about advanced air mobility or advanced aerial mobility. And in particular, there's a lot of hype, as you may know, around the space. And so I'm going to be talking about some of the work that we're doing to address some of these challenges and make this a reality. So in terms of the vision, when people say advanced aerial mobility, this is an artist's rendition from NASA of what we expect. So just broadly speaking, largely autonomous aircraft. It's electric aircraft. They're vertical takeoff and landing because you don't have the ability to build the kind of infrastructure and really moving the kind of commute things that Jinwa talked to the airspace. As an aerospace engineer, ever since undergrad, people always ask, you're at a party and you say you're an aerospace engineer and people ask, where's my jetpack, right? So this is the closest thing to making that dream a reality. But I sort of want to go, and a lot of the work right now, the investment and really the work that's being done is on building the vehicles. I'm going to be talking about some of the challenges in actually making this a reality, right? So having a lot of vehicles together in a system with everything else. Now, it's actually worth noting that there is actually a long history of this transformation towards this, right? So I'm going to go back 120 years. The picture on the left is the Wright brothers' first flight, 1903. This picture that you can barely see is from 1914, and it was a demonstration of one of the first autopilots by Lawrence Perry, who was 20 at the time. And so the way I apologize for the quality of the image, but this was a demonstration in France, and he's got his hands off the controls, Lukma, no hands, trying to fly the aircraft, and then he realized that there was a mechanic on board, and people might think he's controlling the aircraft, so he walked out, and then they actually did a second demonstration with both of them outside, right? So on the wings to prove that no, the aircraft was flying itself. And that's human nature, right? So you want to do things better, and engineers, we try to make things more and more autonomous. In 1947, it was the first autonomous as an unpiloted, manually piloted flight across the Atlantic, right? So we talk about drones a lot now, but if we really think about it, this happened 70 years ago. And of course, it was a mechanical brain, right? It was not even an electronic brain. There were people on board. There was press on board. There were Air Force officers on board, so the amount of trust that goes into doing this. And I actually like that in terms of speculation in the New York Times article, the speculation, what do you do with this technology? And they said, well, there are clearly military applications, but in peacetime, Amazon Prime Air. Right? So we're going to have cargo deliveries and automate that. So much like, what do you do with a vehicle that's autonomous? You can use it to transport it. Of course, this is one aircraft, and it's retrofitting an aircraft that you fly already. When we think about the future of urban mobility, increasingly, especially urban aerial mobility, we have pictures like this. And the aircraft is not that aircraft that we saw in 1947. It's really, aircraft that are much more intelligent in many ways. They're autonomous. They carry passengers. They can carry cargo, all sorts of scales, all sorts of sizes. But we're still building these aircraft. And what we want to do is to have many of these fly in an airspace, which might have, conventional aircraft, might have helicopters and everything else, and how do we do this coexistence? And so that is really the challenge on how do we do this repeatedly, safely, and in a way that actually helps the system performance, right, which is moving things from one place to another. So these, if we think about how much do we expect change? We're thinking about operations, flight operations at an entirely new scale now. When we think about these are going to be autonomous aircraft of many different sizes. There is, of course, a lot of fascination with this. So we're still at the point where we can't quite tell what the reality is going to be. It's going to be somewhere between what the hype is and what will happen, right? And the question is, how much will we be able to support? But some of the projections, so Airbus projects that by 2035, so in another 15 years, we'll have about 20,000 flights per hour over Paris. Just as a point of comparison, Paris now sees of the order of 100 flights per hour, right, in the air. So we're talking about orders of magnitude increases. And we're also, it's similar in the US, especially when it comes to these small UASs or SUAS, unmanned aerial systems. So these are small drones, mostly for package deliveries. And the FAA projected, in 2020 that there'll be 2 to 3 million UASs. Just in terms of the scales of these smaller drones, the number of drones now being sold per month is more than the aircraft fleet that exists, right? So it's just the commercial aircraft fleet. So it's just orders of magnitude change that potentially we would like to support, and the question is, how do we do that? So what are the emerging challenges? And there are lots of challenges, but I'm at the system level and not the vehicle level. There are 3 things that I'm going to sort of highlight today. The first is what I mentioned earlier, namely these are previously unseen, unforeseen many years ago scales of operations. So how do we achieve efficiency at these scales, right? So those examples that I showed of, for example, 1947, that flight across the Atlantic, you pretty much did not have anybody else in the sky at that time, right? So you shut down the airspace. And so even when things like border sorties and things like that happen with unmanned aircraft, you pretty much say there's going to be one aircraft in the sky, I'm going to shut everything down around it and operate. That's a hard enough problem, but you can't do that at scale. You can't have 20,000 flights an hour by saying nobody else flies when this one aircraft is there. So the first question is, how do we even solve these computation problems and answer this? The second is really, it is a very different competitive landscape from the one that the traditional airline industry certainly is used to, where there's been, from 5, 6 of the order of 10 major airlines that operate in any geography, that dominate. They pretty much are all doing very similar things. I mean, yes, they have different models, but they're all trying to transport people or transport cargo and do that across similar business models and similar aircraft. Whereas now we have those, but we also have a huge diversity where what an aerial photography mission might want to do or a disaster response mission might want to do is not going to be the same as a cargo delivery mission, which is doing hundreds of miles, or it's not going to be the same as the person who wants to deliver a toothbrush in the next 15 minutes to somebody in their neighborhood, right? So you want to support this competition, and you want it to be easy for new entrants and new business models really to come in, right? So they can't all look exactly the same. You can't need the capital investment that you would need from an airline in order to even enter this market. So you want to encourage this competition and also support it. But this competition actually leads to its own challenges that need to be considered at the system level as well. The first is privacy, because if you have all of this and you have this increased competition and they're not all doing the same thing, there is competitive advantage to not quite sharing information. There's 2 levels of privacy here. One is the privacy that I care about when there's a drone flying over my house. And that's certainly something that we need to consider as well. And we do consider in our research, but that's not what I'm talking about here. It's almost the privacy that's going to be, that's going to hinder our ability to get efficiency, right? So in order for us to best allocate the airspace and coordinate operations, we need to have information on who wants to fly when. And that information, of course, if you go back to the ride-sharing examples that Jinwa mentioned, Uber and Lyft, right? You don't want the other person to know that this is the place where I have my high demand and I want a lot of operations and so on. So, and this has become very early on an issue because in the US, with these drones, there was a drone ID rule, which is almost like a license plate, right? You have a registration, you got to register your drone, and you put that there, and as soon as they announced it, you know, the companies immediately say, this is a violation of our privacy. And so how do we do that? And also, how do we both improve the privacy? Don't tell us everything. Like we say we need to know everything in order for me to make a system level coordination decision, then that's not going to happen. But at the same time, giving the right amount of information, and how do we incentivize that? And the second one in a competitive landscape, quite naturally, is going to be the issue of fairness. And here it is, again, you know, there are immediately concerns of monopoly, right? So I'm the first person who takes over an airspace. Does that mean that I get to own that and none of my competitors can come in? And really, here, if we're going to have access to new entrants and a wide range of business models, we are going to have to find ways of equitably, in getting that efficiency, also equitably serving different airspace users who might have different priorities. Some people might want to just go round and round in one region of airspace. Other people might want to just take the shortest path out and go and deliver something somewhere, and we need to be able to do both of those. So really the three system level challenges that will help us move us towards that vision are going to be trying to get efficiency, trying to do that with some understanding of privacy and also fairness. So I'm just going to talk about a few things that we do in these. On the first two, with efficiency and doing that with very limited information sharing and giving as much independence or autonomy to the aircraft operators as possible, these really fall into what we would call distributed air traffic flow management, right? So this is coordinating large numbers of aircraft, and I'll go to tell you about that video in a minute. These tend to be very large optimization problems that you actually want to be able to solve in a way where it's not that I have a centralized system operator, you know, be it the FAA or some other air navigation service provider who says, give me all your information and I will decide who gets what, right? So that doesn't work anymore. So what we do, and this is, as I said, is just trying to come up with smart algorithms that we can also distribute in ways that can solve these massive problems very quickly. So this, this movie is a projection of what the FAA in 2014 thought the skies would look like over the US in 2030. So this was 6 years ago before, you know, quite the interest came in. There's the red aircraft are the drones, and so unmanned aircraft, autonomous aircraft, and the blue aircraft are the commercial aircraft. Blue aircraft are, you know, there's about 25,000 flights currently. They were looking at about 40,000 flights then, but they were looking at close to 40,000 unmanned aircraft flights doing various things. So it is a significantly crowded sky. You can see that aircraft do different things. So for example, here there's a lot of aquaculture missions, and you know, there's all sorts of things like pipeline inspections. You might be doing surveillance of fisheries. You could be doing some, there weren't really so many package delivery missions here. There were communication relays, so you know, using aircraft at very high altitudes, autonomous aircraft to deliver. And this sort of problem with, you know, about 80,000 flights in a distributed manner, we can solve now in about over a 24-hour period. We can solve it in about 4 minutes. But if you do it in, you know, next 8 hours, and then I plan again next 8 hours, every 8 hours ahead, you can solve it in under a minute, right? So the idea is that you just have this running, and this is something that is orders of magnitude, as I said earlier, larger than anything that what we would have needed to solve earlier, but you know, we can now solve because we need to solve. So that's the, you know, one piece of it, which is just, can we come up with ways where we can find a solution and coordinate and plan these aircraft safely? The next challenge, of course, is how do you do this when everybody is competing, right? So one is I can sort of do that when I ask for limited information and give them autonomy, but this still doesn't have to be fair. And navigating the efficiency fairness trade-off actually becomes very complex in these networked congested systems. And the reason is the following. One is I can come up with that efficient solution that I came up in the previous slide, right, in that movie. But there might be one operator who is flying across a set of congested sectors, regions of airspace, and we're just going to tell them, yeah, you wait 2 hours and then fly. So because it's efficient for everybody else. So the efficient solution may not be fair. Of course, the fair solution, which is everybody is first come, first serve, wherever you are, it's going to go that way, may not be very efficient because you're just waiting around with nobody using some region of the airspace there. And also, thing about breaking this up is I could be very fair in every queue that I have, right? It's like in the supermarket where if we have many queues we have to go through, and then where every queue is first come, first serve, but at some point, because I had to go through 4 queues, which happened to be busy, I'm going to take much longer to get through than someone who actually had to just do 1 queue, right? So it becomes very different. And then basically also when we have these differing business models, there are many different notions of fairness, right? What is fair in these systems? So we need some ability to measure and develop consensus in that as well. So here in this work, what we've actually started doing is try to build algorithms. So these are almost like protocol-based, so they're sort of like rules of the road, right? So once we have these different things that we might care about, how do we build these rules of the road that can prioritize different levels of fairness? Be it everybody should get equal disruptions or equal delays, or some people are going to get a little bit more delay, but then that extra delay that you get is going to get balanced across your operators, or there's all these different metrics that people can come up with. And so this is actually a collaboration with Airbus UTM, and I think Airbus actually is an ILP member, and we've been working with them. Just this idea of, well, if we can come up with these different metrics and different prioritization schemes, can we look at which ones sacrifice more efficiency, which ones sacrifice less efficiency, and come up with something that might be acceptable to the operators? And we were actually very excited because this past September, this work actually, so the FAA and Eurocontrol have this air traffic management R&D seminar, and we won the best paper there for this collaborative paper with Airbus on this work. So that's one piece. The last take here is not so much fairness to the aircraft operators or the advanced air mobility operators, but going back to the same issue of efficiency fairness trade-offs, but in the context of shared mobility platforms. And so this is actually a collaboration with colleagues in electrical engineering and computer science at MIT. And so the idea here is when you are actually getting benefits out of sharing. So Junwa actually was great because he mentioned this where GREs decides that they're going to use some of it for cargo. So there is a lot of benefit when you actually think about multiplexing, right? So I'm going to be making that trip anyway in order to tell, because somebody is traveling, maybe I should also be doing something else nearby there for someone else. And so you could have these different customers, right, users of the system. And so this is an example of this, not in the, so we look at the rideshare context, but because it's an advanced air mobility thing, I wanted to show an aerial sensing example here, where let's suppose we have 5 drones with some limited battery life, and we have a set of 5 different customers who would like different aerial sensing tasks. So one person wants to monitor traffic, one person wants to keep monitoring parking spots for availability, someone wants to just look at the throughput, the cellular throughput over the airspace, because you actually need cellular connections to reliably fly your drones. Air quality monitoring, which is another thing that increasingly people do, it's very advantageous to do with drones, and then infrastructure inspection. And you have these tasks that are spread out all over a city. The question really becomes, how do we efficiently share this resource of these drones in order to make sure that I'm not doing only one thing, so I'm not only monitoring traffic all the time and not doing any of a different kind of task, but also at the same time not waiting around because I've said I'm going to give this drone is doing nothing but looking at air quality, and so if there isn't that task, I'm just going to wait around doing nothing. And what we're able to show in these systems is that when you have these mix of application properties that you'd need, so some things that need to be monitored continuously, some that you want to go back and just keep cycling through all those points, just keep doing it. Other applications where you need to revisit, some things that are more responsive, where a task suddenly comes up and you need to go and respond to it. You can actually come up with very principled ways of navigating those trade-offs without sacrificing throughput, right? So what you want to do is to get solutions where you're almost satisfying doing the same number of tasks that you would do the most efficient way, but do it in a way where you're not being very unfair, right? So given a choice between two things that I could be doing in order to keep that same efficiency, pick the one that will balance out different people's needs. So that basically, to conclude and leave a couple of minutes, a few minutes for questions, is really what we, a few of the things that we're doing in order to push this vision of advanced aerial mobility. So, and ultimately, the goal is that if we do this and if we can answer these questions, we can now use the vehicles that are being developed, right? So there's a lot of investment, as I mentioned earlier, on the vehicle side, but you can actually have a system that supports these vehicles and provides efficient, equitable, and sustainable airspace access for all the different use cases that people have come up with already, and people will come up, right? Human nature is we'll come up with new things that we can do with aerial mobility and aerial sensing. So thank you very much, and I'm happy to answer any questions. Yeah.
Thank you for the presentation. When you mentioned about France, it reminded me the movie in early 16th, The Phantomas. Maybe you know that. This was the evil genius who every time was involved in the crimes and used the flying machine. And I just curious, do you have any ideas how you will control the crime? Because still in many cities, the crime rating is high. And I think it's the flying machines opens the new opportunities for crime groups.
So that is a... Sure. I think the question is, the potential for crime now that you have flying machines, right? I think every technology has its potential benefits and has a tendency to get misused, right? I do think, so there is research that we do that looks almost at new security vulnerabilities that get opened up because of this. And the privacy case that I didn't mention is one of those, where if I'm actually flying over an airspace and I'm taking images in order to navigate, I have an image of a house. Can I do something else with it? But at so we do look, there are very important research questions that people are looking at which are based entirely around that point. But I think it's important for us to actually look at that no matter what the technology, right? Because every technology that we come up with, somebody can find a way to misuse it. So I think the challenge is figuring out what those threat vectors are and how we would be able to mitigate that. But I think it's a really good question, yeah. Yes?
With separation and being pushed down to the service providers, as well as deconfliction, how do you envision, would every service provider have to pick up your algorithm, for instance, and it worked? Or how do you deal with the fact that there's going to be different PSUs using different methods?
That's a great question. So I think one of those things, one of the fascinating research things that we are trying to understand is actually the service provider dynamics. So how does a service provider work? So just as background for everybody else, for everybody, right now, if you think about it, it's mostly the FAA, or there's, Europe, or in Asia too. There is almost a government, or in some sense, there is a government, a public air traffic control that manages everything. With advanced air mobility, it's really, I think most of the air navigation service providers have said they're not going to be in the business of managing this traffic. And so it's really going to be at the level of the service providers to decide what the separation between this is going to be and how they're going to coordinate it. We think that there are very nice questions here on how a service provider would behave in this, because the service that they provide, if there's enough competition in the service provider space, it's now going to be a question of what is the agreement between the service providers and the aircraft operators. So how much efficiency are you giving me, and what that contract, that service level agreement looks like, and what am I selling? Right? So am I selling safe access? At what level of safety am I guaranteeing that, and so on? So the way we're thinking about it is, how does, and this is an open thing, right? It's nice because we built the vehicles. We don't know how they're all going to fly together. And so there's, I think, a huge potential for thinking about what does revenue sharing look like here? Because do I contract with a much less expensive service provider, but I may not get the same level of safety that I might get from somebody else who is more expensive but gives me a high level of safety. So I think we're trying to, and all of that is going to translate to things like separation, things that the requirements that they impose. But I think it's a fascinating system design question there that we're looking at. Yeah.
This is kind of a similar question. So in terms of multiple uses for the same aircraft in a given time and location, do you think we'll tend towards a more centrally controlled and optimized setup, where you might get guaranteed service, or more of the Uber model where it's opportunistic? You might not get it when you need it.
I think.
The audience probably can't hear.
Yes. So the question is whether with the sharing platforms, we'd move to a more centralized setup, or more Uber rideshare type, decentralized setup. I think in order for this to actually work at scale, we're going to have to support on-demand services. Right? So certainly, if you think about airlines now, if they file their flight plans hours in advance, and you sell your tickets months in advance, and you publish your schedule years in advance, months in advance, right? So you cannot, I don't think at this scale that market is going to come there. We actually, when we design the algorithms and the platform, one of the things we want is that it be responsive to dynamic demand, which will go away. So if you decide that you're sharing and you're not serving something, you're going to lose revenue. And so, but I absolutely, at least this is opinion, right? But I think that if we are going to build a system that's going to work at these scales, a lot of that demand is going to pretty much be something that we're going to have to get dynamic, is going to be dynamic. But there are ways we should think, but if you had more information further ahead, you can make better decisions. So that's where the incentives come in. Much like if I book a ride share earlier, sometimes I get a better guarantee, or I get something out of that. And I think from the system perspective, we should be thinking about that, where we should be able to support dynamic demand, but at the same time, if people actually have that information, maybe, think about how you would incentivize sharing that information, and that could be through how you price the service. Yeah.
So when FAA does this type of service, they do have communication, aviation, and sensing infrastructure.
Yes.
That's not visible.
Yes.
If you move it to private sector, is the current mechanism, are the current mechanisms sufficient to support that, or any new requirement that's coming up?
So I think there is, that's one of the things that with the service providers, so there's two elements. One is there's a requirement currently that these service providers, somebody who's providing services for autonomous aircraft, will be able to plug into the FAA's systems and share information with them and get information back, right? But not the aircraft themselves. The service provider will tell them, well, there are autonomous aircraft flying here, so that if the FAA had to say, well, I need this region of airspace, they can actually get the more discretionary demand of at that time. That's on the regulatory side. But one of the questions that exists is there are service providers who might potentially not work on traffic management, but will work purely on the communication, navigation, and surveillance side, where the service that I provide is just where the rest of the traffic is, or being able to communicate that. So I think this goes back to the question of what is the service that I'm selling. And I've been focusing on the traffic management side of the service, but there's certainly communications is a service that I can sell, right? Much like a cellular provider. So.
Thank you. All right.
Thank you.